Alright, so let me bring up Lab 1. You can download this from Canvas. And it's a looks like a long lab. It's 9 pages, but that's really just to have enough detail in here so that you don't have to figure out too much stuff. It's really meant to kind of like spell things out for you and give you a quick start on the things we're going to do in all of these labs. The labs are an important part of this course. You've got to do the labs in order to learn the material, and you've got to get a C or better on the lab average in order to pass the course. So this first lab is worth spending as much time on it as you need to go through all the steps, get all the steps to work the way they're supposed to work. And then future labs get a little bit easier because we know sort of the mechanics of assembling our programs using the debuggers. Alright, so this first lab is basically getting used to the command line based development tools. We're using a different tool set from what we've used in the past for this course because the software we were using before is not accessible. It doesn't work well with screen readers and such, so we've retooled it, and we've got some new command line interfaces to the underlying tool chain, and so that's what this first lab goes through. There's one experiment. It's the introduction to all of this. Basically, you're going to write a small assembly language program. You're going to assemble it, simulate it using these command line tools. You'll make a test bench to implement a test plan and things like that. So let's go through these steps here. Go ahead and log into the Linux system. I strongly recommend being organized in your hierarchy of files. So for example, let's make a 370 subdirectory, and I'll go into there, and let's make a subdirectory for labs, and I'll go into there, and I'll make a subdirectory for lab 1. So I'm sitting, you know, under this hierarchy, and then when I work on lab 2, I can go into lab 2, and it's totally separate from lab 1. Right, here's my lab 2 assembly program. If I go into lab 1, I've got a separate set of files. So make a hierarchy so that you can keep your files around, go back and refer to them, and so on and so forth. Alright, so we're in the Linux machine. You've got yourself in a good directory to work. Here is the sample assembly language program that we're going to work with. Now, most of the labs will have sample code for you. The sample code is meant to be a reference. You can look at it, you can go through it, you can ask questions about it, and it can help you to understand some of the concepts involved in doing the lab. But in general, you're not just going to want to take this and copy and paste it and start modifying it. You might want to take bits and pieces of it, but don't spend all your time trying to figure out how to turn the sample code into your lab. Use it as a guide. Use it as a reference for an example of some of the things you might want to do, but write your own code from scratch. But lab 1 is different because we haven't had a chance to go over any programming concepts for assembly language, so for lab 1 you're expected just to use this code exactly as it is. Now if you try to copy and paste it from a PDF, it usually doesn't work, but you can find a copy of it in this directory. Use your local data BSCS 370. So I'm just going to copy from there, copy user local local data BSCS 370, and there's one file in there right now, lab1 samplecode.asm, and I'm going to copy that into a new file. I'm going to call it lab1.asm. Alright, your assembly files are always going to want an extension of .asm for assembler. And now we're going to edit this file just to look at it. We're going to use the VI editor. You can find other editors. I strongly recommend getting good with VI. There's a video here linked in the lab that you can watch to get some hints on doing more with the VI than just moving around with the arrow keys. But let's just go ahead and hop in here and take a quick look. So This is basically the same code that's in here. It's 49 lines of code. We do not need to worry about the details of what's going on in here. I do want to point out though, there's this thing called count, which is defined to be 0x080. It's named count because it's counting something. And there's two ports, port A and port B, and we are using port A as an input, and we're using port B as an output. So keep those in mind as we experiment with this. Alright, so we've got our program, and this is human readable if you know how to read it, but the PIC processor cannot do anything with it, so we need to convert it into the ones and zeros that the processor can actually understand. And we do that with the assem command, ASSEM. If I just say assem, it'll tell me, hey, you have to say assem followed by the name of a file. And you can put the .asm extension if you want, or you can leave it off. So I'm just going to say assem lab1, and it says success. That's great. If I made a mistake, for example, if I said move WF ris A, and then I try to assemble it, I'll get an error message, right? And here it says ris A is a symbol it's not previously defined. All right, so you go in there. Oh, and it tells you, you know, this is line 28. So I can say 28G and get down to line 28, and then I can look at ris A, and it's like, oh, that's supposed to be tris A. I deleted my T. Okay, so I'll put that back in there. I'll reassemble it, and it says success. By the way, I'm using the arrow keys to go back to previous commands. You don't have to do that. I sometimes watch students spend, you know, a minute trying to get back to a command that they ran before, and the command is like 5 characters. There's nothing wrong with, you know, just typing assem lab1 again. But if I wanted to do that immediately after, I can just up arrow and get to that same command. Alright, so we assemble it. It said success. Great. Take a look in your directory. We've got a few files here. This is the file that we started with. This is the file that will contain any errors. If there's no errors, this is empty. This is the file that will get loaded into the PIC processor. This is what we call a disassembly listing file, and this is an object file we're not going to worry about. So take a look at this lab1.hex. It's hex characters, but it's actually locations and data that should get stored into those locations. Alright, the more interesting file for us is this listing file, and let me make my window a little wider for this. This is called the disassembly listing. It includes a copy of your original information over here. It's also got line numbers on each line, which is useful. It's also got more of these hexadecimal numbers on the left side here. What we're seeing is down here we're seeing a memory location and a set of data stored at that location. Every 2 characters corresponds to one 8-bit number. So location 0 contains a 6A, location 1 contains an 80, and then location 2 is 6A, 3 is 81, and so on. And as we go through here, you can see some of these have 8 characters, so this is location 16, 17, 18, 19, and then location 20, which is actually 1A, would be down here, 1B, 1C, and so on. So all of this is hexadecimal. Brush off your hexadecimal skills if they're rusty. But this is the machine code that corresponds to these instructions. We're going to get into all of this in a lot of detail down the road, but right now the main thing to know is that each of these things generates some machine code which is stored in memory at these addresses, these locations. So this is a useful file, and you always want to include this in your lab report, right, as opposed to just the raw source file. When you do this, I strongly recommend experimenting with your word processor. Find a monospaced font so that things line up. Make sure it is single spaced. Don't double space it. That's the default for a lot of things. It wastes a lot of space in your report. Also, down here, we've got the last line of the program, and then there's this thing that says symbol table, and this goes on for hundreds of lines. Don't put all of that into your file, right? So maybe edit it, search for that place that says, edit the listing file, search for that place that says symbol table, delete everything from there on down, and now we've got a relatively small file. Alright, so that's the disassembly listing. This is going to be useful when we debug. Alright, so you can read all of that in here. Let's go ahead and do our debugging. So to debug, we're going to say debug lab 1. And that's going to bring us into a tool that is able to take commands from us and simulate the behavior of this program. So there's all of this startup information. It resets the processor, it specifies the device, that's the chip we're using, sets up hardware simulation, sets the system to be a 32 kilohertz clock. We'll get into clocks later. And then when it's all done, it gives you this message, debugging begins, and it gives you the current date and time. At this point, we can do a number of things, and there's some commands listed in here. We can say run the program, stop the program, step 1 instruction, step 100 instructions, print the value of a location in memory, either by name or by address. 0x20 means hex 20. We can drive the values of certain pins high or low by saying write pin, the pin number, and saying high or low. We can set a breakpoint, so if the program gets to this line, this address, it would break. So if I said break 30, whenever the program got down to this statement, which is at address 30, if it's running, it will stop and it'll say, hey, I hit line 30, I'm taking a break. We can also watch a location, and the W says, hey, if that location gets written to, stop the program from running any further and tell me that just got written to. We can sleep for a number of milliseconds, so if I sleep 2000, that'll sleep 2 seconds. We can echo a message, which just, if I say echo hello, it just says hello. And we can quit with the quit instruction. Alright, so we are debugging lab 1, and it gave me the message saying, okay, debugging begins. Let's take a look at port B. And you can get away with uppercase or lowercase on these names like port B. Okay, port B is 0. Let's step the instruction. And it says it's step to address 2. And if I say step I again, and I'm using the up arrow to get back to that command, it goes to address 4. And if I do that again, it goes to address 6. If I just hit enter, it'll repeat my last command. So I can go to 8, and then A, and then C, and E, and 10, 12, 14, 16, and I can keep doing this. I'm just hitting the enter key. So if I look at this and I pay a bit of attention to it, it looks like it's looping. It's doing 1.6, 1A, all the way up to 2A, 2C, and then back to 1.6. Right, so it looks like it's in a 9 instruction loop from 1.6 out to 2A, or sorry, to 2C. Let me go ahead and log in a second window here. And let me go back into our listing file. And we're looping from 1.6 down to 2C. So what is instruction 1.6? It's right here. Hey, it's a thing that says loop. And what is 2C? It's a thing that says go to loop. So we are executing this set of instructions over and over and over again between here and here, right? And it's called a loop, right? So we'll learn all of these things as we get into assembly language, but right now we're just observing that as I step, I continue to go between those sets of instructions. Okay, what happens if I change RA0? If I print port A, it's a 0. If I write pin RA0 high and I print port A is now a 1. Let's go back to stepping one instruction at a time. There's 24, 26, 2A, 2C. Same business as before, but suddenly I'm somewhere else. I'm at address 30, I'm at address 32, I'm at address 34. I have jumped down to this new set of code. I didn't do my goto for some reason. So this is intentional, and as we do this, and we keep stepping, eventually we find we're back to this loop between 1.6 and 2C. But now if I were to print port B, it's gone up to a 1. And if I make my pin low and I step a bunch of instructions and then I print port B, it's gone up to a 2. If I make my pin high and I step 100 times and I print port B is now a 3. Alright, so port B is increasing every time that we toggle this pin RA0. That's the basic behavior of the program. Stepping like that is useful when you're really trying to narrow down exactly what's happening in some section of your code, but it's pretty inefficient. So a more efficient way to work with this debugger is just to say run. And when you say run, it says running. It means it's executing instructions in the background. And it doesn't look like it's doing anything different, but for example, if I say print X PCL, PCL is the address of the instruction being executed. X says printed in hex. It goes from 1A to 24 to 16 to 1C. It's executing this loop again. And every time that I say print PCL, you know, it's whatever instruction happens to be at when I ask it to print. So this is running very fast in the background right now, but we don't really notice that. Right now I can say stopwatch, and it will tell me how many instruction cycles have been executed. And it looks like this is 74 million. If I say stopwatch again, it's 88 million. So it's doing a lot of work, and it's running for a simulated time of 11,000 seconds. So coming up on 4 hours. Very fast simulation. All right, so it's running right now. And if I print port B is still a 3. If I change my pin to be low and I print port B, it's a 4. If I change my pin to be high, it's now a 5. If I change it to be low again, it's a 6. So I can very efficiently change the values of inputs and observe the values of memory locations or outputs while the program is continuing to run in the background. So that's a more efficient way to debug. Another option is to set up breakpoints or watch points. So for example, we noticed when we broke out of the loop, we jumped down here to location 30. We could set a breakpoint at location 30, and every time that we get to that instruction, it will stop what it's doing and come back and tell us, hey, I'm at location 30. We can also set up a watch point. So while we're incrementing port B, we're also incrementing file location 80. 80 is this count, and the count is what's actually getting copied to port B. So we could put a watch on location 80, so I can say watch 0x80 for writes. And now if I set this high, it tells me, hey, location 80 just changed. I'm going to stop the simulation and wait for instructions from you. And if I print location 0x80, it's changed to a 7. If I say run, it continues running. This is still a 7. But now if I toggle this pin again, it stops again and says, hey, location 80 changed. And if I print it, I can see it changed to an 8. And if I do a break, let's say I put a break at location 30, which is this place where we come out of the loop, and I say run, and now I toggle my pin again to make it high, it says, hey, I got a breakpoint at location 30, right? And if I say print PCL, it tells me PCL, the instruction that I'm about to execute is 30. That's this instruction right here. So breakpoints and watch points can help us run a lot of code, but then have the simulation stop when something that's interesting to us happens. So that's just part of your standard debugging toolkit. All right. So the last thing is this idea of a test bench. So we can do all of this, right? But this is madness to go back and try to understand, and you don't want to take all of this and stick it in your lab report, because it's got, you know, missteps, and it's got things that we're doing to try to understand what's going on in different experiments and so on. So let me quit out of here, let's talk about test benches. So if you've done CSE 250 recently, you probably used test benches with Verilog. A test bench is really just a set of instructions that you're going to use to stimulate your circuit or your program and get certain expected behavior out. And this makes no sense unless you have a test plan. So 250, you're supposed to have a test plan for each of your lab experiments. Not everybody did that. We definitely want to do that in here. So what did we do? We were exploring this program, and we started changing RA0 between low and high, and we found that if we did that and we stepped enough times, we would get a change in the value of port B. And if we didn't do that, we would just sit and loop among 9 instructions in the beginning until that port changed. So we want to capture that behavior, right, to know if our program is doing the right thing. Now, future labs, you're going to write a program to control a traffic light, so you'll come up with your own test plan for that. For example, I'll set this pin high to simulate a car coming to the south, and then I'll step the simulation and I'll look to see this output, which means that the south light is green. And then I'll set this input to make a car on the east, and then I'll step it and wait for this output, which says, you know, the light is going yellow on the south or whatever. So for this test plan, for this lab, it's pretty simple, right? We just want to do some of what we've been doing in this window right here. So you can read the details of this in here, but basically we're going to toggle port A, we're going to monitor port B, and we're also going to monitor location 80. We're going to see that we're in a loop, we break out of the loop, we increment those locations. Alright, so what's a test bench? It's really just a script of commands. But the idea is, you're working on a piece of code, you want to know if it's correct or not, you just run it through this test bench, you run it through this script, and you expect certain behavior out. It saves you from having to type in all of this stuff every time and keep track of what's supposed to be happening every time that you make a change. Or in particular, if you come back to this a few months down the road and you've got a new piece of code and you want to know if it still works, you can just run it through the test bench. Alright, so here's a test bench that works well for this. We'll start the program, we'll step 20 times, and then we'll step 9 times and watch what happens to the simulator, and we'll see that it's looping. And we'll check port B, that should be a 0. And then we'll set RA0 high, and we'll step, and we'll notice that we come out of our loop. And then we'll continue stepping until we go back into our loop, and we'll check port B, and we'll see that it's incremented. and then we'll toggle RA0 again, step a bunch of times and watch port B, and it should increment again. Set this high and it should be incremented a third time, and location 80 should also be incrementing as we do this. Alright, then I'll set it low, step some more, look at port B and location 80, and we should see that they've both incremented. And then we'll set a watch point. So we'll put a watch on port B. We'll run the program for a while. Now, this script will run very quickly if I don't tell it to wait along the way. So after I say run, I want it to actually get through some of the code before I go ahead and turn this pin high again. So I'm going to say sleep for 1 second and then set this pin high. And I want to wait a little bit of time. I don't need a whole second, but I'm going to wait a second before I look at port B, and port B should be incremented at that point. And then at that point I'm just going to quit. Alright, so I don't want to type all of these commands in, so I'm just going to highlight all of these. I'm going to hit Control-C to copy, and over here I'm going to make a file called lab1.bench, and on my system I can do Control-Shift-V to paste that in. So now I've got a copy of my test bench in this file lab1.bench. Alright, how do I feed that in? Well, I can put what's called a switch on the debug command. I can say debug-testbench, put in the name of the test bench file, and then say lab1. And if you just say debug, you'll see all the options. I can say speed, test bench, and log. So I'm going to debug test bench lab1.bench, and the file I'm debugging is lab1. But it's still a lot of output to take in. So I want to save this output. And we can do that by using this -out switch. So if I do that, and I combine it with the -test bench, I can put all of this into an output file. I can do this in any order I want, so I'm going to say -out lab1.log. And it'll still show me all of the output on here, but when I'm done, I'll have a new file called lab1.log that'll have a copy of all of this output. Okay, so let's look at lab1.log and see what we just did in the test bench. This was all set up here. We programmed the device debugging started right here. We stepped 20 times, that got us to address 16. We noted this is a 9 instruction loop. We stepped 9 times and it went 16, 1A, 1C, 1E, 20, 24, 26, 2A, 2C, and then back to 16. We checked the value of port B, it was 0. We wrote RA0 high. We started stepping again, it did 1A, 1C, 1E, 20, 24, 26. But now it went 28, 30, 32, it broke out of the loop. So now we stepped 20 times and we got back to location 2A, so we're back in our loop, but when we checked port B it changed from a 0 to a 1. Now we set RA0 low, we stepped 50 times and port B is a 2. We set RA0 high, step 50 times, and port B is a 3. So this is illustrating that every time we toggle RA0, port B goes up by 1. Location 80 is also changing, that's currently equal to 3, which is the same as port B. Set RA0 low, step 50 times, 80 is 4, port B is 4. So they're both incrementing together. So that's another observation. And then we set up a watch point just to illustrate what watch points do. So I put a watch on port B for if it gets written. I said run. I slept for a second and then I toggled RA0 high and waited a second, and the simulator said, hey, there's a breakpoint. It said F81, that is what port B is. We'll learn why that is later. But it halted the simulation because my watch point fired. Port B changed. If we look at port B now, it's changed from 4 to 5. So that's how a watch point works. That's the end of the simulation, and we're done. Alright, so a lot of information in here, right? But this is a process you'll go through over and over, and the more you get used to it, the more the mechanics kind of go by the side. You don't have to worry about all of those mechanical details. You worry about the actual code that you're developing and the actual testing that you're doing. Um, and so this is just practice with some of these ideas. All right, so for lab one, the requirements, you got to do your lab report individually, as well as the lab. I'm okay if you want to, like, you know, be working next to somebody and you know, ask questions, or hey, what does this error mean, or hey, what was that command we were supposed to do, or that kind of thing. But you should be doing this lab yourself, right? You don't have to be in perfect isolation, but don't sit there and watch while somebody else does it, and then take their results and put it in your report. I want everybody in the course to be actually doing the lab themselves, and the reports have to be individually generated. Reports have to be computer printed. If there's a formula or a diagram that you need to draw by hand, you can do that, but everything else should be computer generated. Things like this output you can copy from the file and paste it into your favorite word processor, but again, find a monospace font, make sure it's single spaced between the lines. Consider shrinking it down as small as 8 point, to make it fit better on the page, and so on. For each experiment, describe the problem in your own words. What are you doing? If there's specific questions that it asks, make sure you answer those. We're not writing the code for lab 1, we're given the code, but going forward we would want to develop pseudocode to describe the code that we're implementing. So pseudocode is like a high level version of it. You can write it in something like C, but it's not code, it's not C code. It's a human readable description of the algorithm, not the program. And we talk about this in some of the other videos. Include your disassembled code, which is that .lst file, and then your simulator output, which shows the debugging command, memory locations, and so on. That's what this output file is. And you choose what you want to print, what you want to look at, what commands you want to use when you put up your test bench, which is based on your test plan. And then for the report as a whole, cover sheet with your name, date, the class, and so on the front, an introduction to the lab in the beginning, and at the end a lessons learned section which summarizes what you learned. And try not to just say, I learned how to do assembly language, I learned how to use the debugger. What did you learn beyond, you know, the steps that were given to you? Oh, I learned how to use the up arrow key to repeat commands. I learned that uppercase doesn't matter on some things, but it does on others. Right? Think somewhat deeply about this. What are your takeaways from this? Don't just say, I learned how to run a program that increments port B whenever port A bit 0 changes. Right? What did you learn from this? And then, really important, a new experiment section has to come at the end, where you come up with a new experiment, and you do that experiment and you write it up. And this has to be a full-blown experiment. You can't just say, change a line in the program and rerun it, see what it does, right? That does not have enough detail. If I gave you that as an experiment, you would be upset, because it's like, well, I don't know what line I'm supposed to change. How am I supposed to change it, right? Put in all the details that you need for somebody to do the experiment, and then do it, and then write up that experiment. All right? And do not just modify the experiment that you've done, or an experiment in a future lab. Take a peek at the future labs, see what they are. Don't replicate one of those, right? So don't just say, let's change this so that it uses bit 1 of port A instead of bit 0. That's a minor change, right? And for lab 1, we haven't really gone over programming details yet. So your experiment's probably going to be something related to the assembler or the debugger. So maybe do some testing of those options. See if you can figure out what happens when you change the speed, for example. Um, think about it. I'll be pretty forgiving on lab 1 because we don't have a lot to work with, but as we go forward, I'll be expecting more and more out of you in terms of the new experiment you come up with. Alright, that's a long, wordy discussion of lab 1. It will take you perhaps less time to do the lab than it takes you to listen to this whole video. That's okay. But anyway, that's an overview of the debugging tools, and like I say, we'll be using those throughout. So when you're done and you want to log out, you can say exit, or you can say Control D, and that'll take you out of PuTTY or back to the place where you did your SSH. Alright, that's a good start on lab 1. I will catch you all later. Thanks.